The speed of light, a constant etched deep into the foundations of modern physics, is often presented as an absolute limit of the universe, a velocity that no matter can surpass, defined precisely as 299,792,458 meters per second in a vacuum, a figure that physicist Albert Einstein placed at the center of his special theory of relativity. Indeed, in everyday experiences and within the framework of classical physics, it appears nearly infinite, sufficient to circle the Earth 7.5 times in just 1 second, a feat beyond the capabilities of any artificial vehicle humans have ever built. However, as we extend our gaze beyond the fragile atmosphere of our planet, reaching into the vast expanse of the cosmos that we describe as endless, that seemingly unimaginable speed suddenly feels astonishingly slow, a relative slowness that stuns when confronted with the immense scales of cosmic space and time. To truly appreciate this contrast, we must anchor ourselves in the astronomical units that astrophysicists employ daily, units that far exceed familiar kilometers or miles. The first fundamental unit is the astronomical unit, defined as the average distance from Earth to the Sun, a span that light takes approximately 8 minutes and 19 seconds to traverse. This number, though modest on the cosmic scale, serves as an essential measure for our solar system. Even at light's terrifying pace, sending a simple radio signal from Earth to the Voyager 1 probe, wandering at the solar system's edge, requires a noticeable delay, a lag that mission controllers at the Jet Propulsion Laboratory in Pasadena have grown accustomed to, a constant reminder of the physical distances they strive to overcome. Recent observations from the James Webb Space Telescope, launched in 2021 and now delivering unprecedented images of distant stars and planets, have further refined these measurements, revealing subtle variations in solar system dynamics that highlight how even nearby journeys test the limits of light speed. Yet when we venture beyond the Sun's influence into interstellar space, units like the astronomical unit quickly lose relevance. Here, the light year emerges, defined as the distance light travels in 1 Earth year, an enormous stretch equivalent to roughly 9,460 billion kilometers, a figure that mathematicians sometimes express as 9.46 times 10 to the 15th power meters. Our nearest stellar neighbor, Proxima Centauri, a dim red dwarf in the Centaurus constellation, lies about 4.24 light-years away. Thus, even traveling at light speed, regarded as the universe's absolute maximum in physics, would demand more than 4 years to reach that closest neighboring star, a duration lengthy for human perception, especially since those 4 years represent the cosmic speed limit itself. In 2025, astronomers using the Vera C. Rubin Observatory in Chile have begun mapping billions of stars with unmatched precision, including Proxima Centauri, providing fresh data on its flares and potential habitability that underscores the practical challenges of such journeys. This reveals the core of the relativity at play: light speed, however swift, lacks instantaneity in the cosmic context. Envision the most advanced space probe we can imagine, equipped with cutting-edge propulsion based on current physics theories, capable of sustaining a substantial fraction of light speed, say 0.1 times that velocity, or 1/10 the universal limit. Even at that astonishing rate, reaching Proxima Centauri would consume more than 42 years, a voyage spanning nearly a typical human career. Advancements in propulsion concepts, such as ion thrusters tested on NASA's Dawn mission and now evolving toward nuclear thermal systems under exploration by the Space Nuclear Propulsion Project, offer incremental gains but still fall far short of bridging these gaps without relentless innovation. As we push further afield, light slowness grows more pronounced. Sirius, the brightest star in our night sky, sits about 8.6 light-years distant. Consequently, the light we see tonight from Sirius actually depicts the star as it existed 8.6 years ago, a genuine time delay, a window into the past. When astronomers observe remote objects, they do not witness them as they exist now but as they were in distant eras. This is no random effect but the inherent nature of finite light speed in infinite space. The James Webb Space Telescope's infrared capabilities have captured stunning views of Sirius's companion white dwarf, revealing details of its cooling process that echo light's temporal lag, allowing scientists to model stellar evolution with greater fidelity. For more distant star clusters, such as the globular cluster Messier 13 in the Hercules constellation, a massive sphere of hundreds of thousands of ancient stars, the distance stands at approximately 25,000 light-years. For light from the farthest stars in that cluster to reach the Hubble Space Telescope or the James Webb Space Telescope, it has traveled through space for longer than the recorded history of human civilization. Analyzing the spectra of these stars amounts to cosmic archaeology, unearthing light traces from an epoch when early humans had yet to master fire. In 2025, the Atacama Cosmology Telescope has delivered high-definition maps of the cosmic microwave background, enhancing our understanding of these early stellar populations and their role in galaxy formation, adding layers to how we interpret light's ancient messages. This slowness intensifies when considering our own galaxy, the Milky Way. Its estimated diameter spans about 100,000 light-years. This implies that light from a star at the galaxy's farthest edge requires 100,000 years to reach our Sun's position. If we could fire a powerful laser beam from one galactic end to the other, that beam, despite carrying the universe's maximum speed, would need 100 millenniums to complete the trip. The contrast between the attainable maximum speed in the universe and the physical scale of cosmic structures ranks among the most captivating paradoxes in astrophysics. Recent simulations from the Dark Energy Spectroscopic Instrument Collaboration, analyzing over 6 million galaxies, have mapped the Milky Way's structure in 3 dimensions, illuminating spiral arms and dark matter halos that make these vast distances even more tangible. Venturing beyond the Milky Way, the narrative grows more spectacular. Our nearest neighbor galaxy, the Andromeda Galaxy or Messier 31, resides about 2.53 million light-years away. The light we observe from Andromeda in its most famous images departed that galaxy 2 million years ago, when the human genus Homo was just beginning to evolve on Earth. If a catastrophic event unfolded now at Andromeda's core, we would remain unaware for over 2 million years, as that news, carried by photons, remains bound by light speed. The Vera C. Rubin Observatory's legacy survey of space and time, set to scan the entire visible sky every few nights over 10 years starting in 2025, promises to track Andromeda's motion toward us, refining predictions of its inevitable collision with the Milky Way in about 4 billion years. We then encounter the observable universe's boundary, a crucial concept defined by the universe's age and light speed. The universe is estimated at approximately 13.8 billion years old, originating from the Big Bang. Thus, any light reaching us today has traveled at most 13.8 billion years. This defines a spherical observable universe around us, the space we can survey. The farthest observable distance, known as the cosmic horizon, extends about 46 billion light-years in every direction, though this figure complicates due to space's expansion. To clarify the 46 billion light-year mark, we must incorporate cosmic expansion, a notion derived from Einstein's equations and confirmed by Edwin Hubble's observations that galaxies recede from us at speeds proportional to their distance. While light travels at light speed, space between galaxies can expand faster than light. This does not violate special relativity, as no matter moves through space faster than light, but space itself expands. Galaxies emitting light we see today, 46 billion light-years away, actually recede from us faster than light due to accumulated expansion during the photon's long journey. In temporal terms, light's slowness proves utterly evident. Consider the cosmic microwave background radiation, the Big Bang's thermal remnant, first detected in 1965 by Arno Penzias and Robert Wilson. This light, essentially microwaves, has traveled 13.8 billion years to our antennas. It depicts the universe at merely 380,000 years old, the recombination epoch when neutral atoms formed first, rendering the universe transparent to radiation. Light speed, though rapid, required over 13 billion years to deliver news of that primordial moment. New analyses from the Planck satellite's data, combined with 2025 observations from the Simons Observatory, have detected subtle asymmetries in this background, including a stronger-than-expected dipole and hints of quadrupole variations, suggesting early universe turbulence that influences galaxy formation today. This slowness poses profound challenges to humanity's aspirations for interstellar or intergalactic travel. Sending a spacecraft to the Andromeda Galaxy, even with hypothetical technologies far beyond current capabilities, such as near 100% efficient matter-antimatter drives, would face a millions of years journey. Assuming a vessel sustaining 0.9 times light speed, an engineering marvel beyond imagination, the trip to Messier 31 would take about 2.8 million years, accounting for space-time dilation and expansion effects. For crew aboard, time might pass slower due to relativity, but for Earthbound observers, nearly 3 million years would elapse. Emerging concepts like the Alcubierre warp drive, revisited in 2025 with positive energy models reducing exotic matter needs, hint at bubbles of warped space enabling effective faster-than-light travel without local violations, though energy demands remain equivalent to Jupiter's mass. This slowness also shapes our grasp of other physical phenomena. Examine gravitational waves, ripples in spacetime predicted by Einstein and first directly detected in 2015 by the Laser Interferometer Gravitational Wave Observatory. Observations of black hole mergers show these waves propagate at light speed. Detecting a gamma-ray burst and gravitational wave from a distant cosmic source simultaneously, any minor arrival time difference provides strong experimental evidence they share propagation speed, namely light speed. Yet from hundreds of millions of light-years away, this synchronization merely confirms they traveled at that pace over eons. The LIGO-Virgo-Kagra collaboration's 2025 announcement of the most massive black hole merger ever, yielding a 225 solar mass object, has yielded waves matching predictions, reinforcing light speed's universality across messengers. In theoretical physics, though light speed stands as an absolute limit, scientists persist in seeking loopholes or workarounds. One heavily discussed idea involves hypothetical particles called tachyons, always moving faster than light. Per relativity equations, zero rest mass particles travel at light speed, non-zero rest mass one slower. Tachyons, if real, would possess imaginary rest mass, requiring faster-than-light motion to conserve momentum. Yet no reliable experimental evidence exists for tachyons, and their detection would demand fundamental revisions to causality, as faster-than-light objects could send information backward in time, shattering the principle that causes precede effects. Another approach to bypassing light speed involves manipulating spacetime structure, like wormholes or Einstein-Rosen bridges. General relativity permits shortcuts through spacetime linking distant points. Stabilizing a traversable wormhole might allow near-instant travel from point A to B, even if conventional space spans billions of light-years. The catch lies in keeping a wormhole open, requiring exotic matter with negative energy density, a quantum-scale possibility, but scaling to macroscopic sizes poses technological and physical barriers far beyond current horizons. 2025 simulations using quantum field theory have explored micro-wormholes in laboratory analogs, offering glimpses into stability but no practical breakthroughs. One cannot omit the warp drive, particularly the Alcubierre model proposed by physicist Miguel Alcubierre in 1994. This avoids local light speed violations by forming a warp bubble around the craft, space ahead contracts, behind expands, propelling the bubble effectively faster than light relative to external references. Mathematically valid within general relativity, the Alcubierre drive still demands vast negative energy, with recent calculations indicating needs equivalent to multiple Jupiter masses, rendering it impractically distant despite theoretical allure. In August 2025, researchers unveiled a physical warp drive model using positive energy solitons, marking a step toward feasibility without exotic matter, though prototypes remain decades away. Returning to light speed's reality amid expanding cosmology, we confront its slowness. Scientists estimate the current expansion rate, via the Hubble constant, at approximately 70 km per second per megaparsec, where 1 megaparsec equals 3.26 million light-years. Thus, a galaxy 1 megaparsec away recedes at 70 km per second from space expansion. At 500 megaparsecs, recession reaches 35,000 km per second, substantial yet far below light speed. As distances grow, cumulative expansion exceeds light speed, explaining the 46 billion light-year horizon over mere 13.8 billion years of light travel. 2025 measurements from the James Webb and Hubble telescopes have refined the Hubble constant to 70 km per second per megaparsec, easing prior tensions and bolstering the standard model, though debates persist on dark energy's evolution. This slowness carries profound implications for extraterrestrial life searches. Suppose an advanced civilization in a galaxy 500 million light-years away sends a message. It takes 500 million years to reach us. Detecting it today yields information from 500 million years past, by which time that civilization might have advanced, declined, or vanished. This questions interstellar communications, meaning we converse with history, not the present. The Search for Extraterrestrial Intelligence project exemplifies this enduring, often fruitless hunt, listening to sluggish photon echoes from afar. In 2025, SETI integrated AI via NVIDIA GPUs for real-time radio signal analysis, tripling detection efficiency and scanning for laser pulses, while revising post-detection protocols to centralize verification amid discoveries like the interstellar Comet 3I/Atlas. Energetically, light speed forms an effective barrier to space travel. Relativity's energy equation shows that as a massive object nears light speed, its relativistic mass approaches infinity, demanding infinite energy. Hence, only zero-rest mass particles like photons achieve light speed. Propelling any spacecraft, regardless of size, by any means encounters this escalating energy demand. Attaining, say, 0.999999 times light speed requires fuel exceeding Earth's total energy reserves, a practical impossibility. China's 500-meter aperture spherical telescope, operational since 2016 and enhanced in 2025 for SETI, exemplifies efforts to overcome these limits by probing faint signals. Moreover, light slowness influences our physical model's construction. In modern particle accelerators like the Large Hadron Collider at CERN, protons accelerate to 99.9999991% light speed. Even there, the gap to full speed demands precise calculations for subatomic dynamics. 2025 runs at the collider have probed Higgs boson decays, confirming light speed's role in quantum field interactions. Even in cosmology, light slowness shapes macroscopic space understanding. Mapping galaxy distributions yields three-dimensional space charts, but truly, these map spacetime, with the fourth dimension as light's travel time to us. Observed superclusters and cosmic filaments formed billions of years ago. Finite light speed ensures structural changes take millions or billions of years to reach us, rendering large-scale dynamics observation exceedingly difficult and demanding extraordinary scientific patience. The Dark Energy Spectroscopic Instrument's 2025 data release, covering 11 billion years of expansion, has revealed early galaxies' contributions to the cosmic microwave background, blurring lines between primordial glow and stellar afterglows. Consider quasars, dazzling active galactic nuclei at vast distances. The brightest shine from over 12 billion light-years away, depicting them 1 billion years post-Big Bang. Their light has traversed an expanding, cooling universe, passing giant gas clouds and infant galaxies. Light speed, as cosmic messenger, has stretched event evolution for telescopic study. 2025 discoveries of the most distant odd radio circle, nearly 10 billion years old, via radio telescopes, have unveiled double-ringed structures challenging formation models, attributed to light's delayed delivery. This slowness fuels cosmic loneliness. Though the observable universe holds hundreds of billions of galaxies, each with hundreds of billions of stars, communicating or visiting other civilizations proves nearly impossible on humanity's timescale. A standard laser beam takes millions of years to reach Milky Way neighbors, and millions more for replies. This erects an impenetrable time wall from finite light speed. Yet optimism persists. 2025's detection of a super-Earth 20 light-years away, orbiting in a habitable zone, via the TESS mission, heightens prospects for biosignatures, potentially shortening effective distances through shared evolutionary insights. In quantum physics, though microscale interactions seem instantaneous, this holds only in flat spacetime frameworks and prohibits useful faster-than-light information transfer. Quantum entanglement, where linked particles' measurements instantly affect distant partners, appears to defy light speed but cannot transmit information, preserving causality per special relativity. 2025 experiments with entangled photons over kilometers have confirmed no communication theorems, reinforcing light speed's quantum guardrails. Nevertheless, light speed in vacuum remains a foundational constant. a greater value would reshape our universe. Stars would exhaust fuel far quicker, lasting mere millions of years instead of billions. Intelligent life as we know it might lack development time. Thus, light speed's relatively modest value against cosmic scales proves essential for our existence, a fine-tuned prerequisite. In summary, light speed, defined as 299,792,458 meters per second, stands as an ideal, inviolable physical constant in vacuum. Yet applied to the universe's colossal scales, it unveils astonishing slowness. Intergalactic distances, measured in millions and billions of light-years, render information transmission, whether natural light or artificial signals, a process spanning eras. Gazing at the night sky, we peer into the past, constrained by this cosmic messenger's slowness. That slowness, a barrier to interstellar travel, simultaneously enables the existence and evolution of all we know, potent evidence that light speed, however swift, imposes an invisible yoke on our comprehension and access to the cosmos's unfathomable vastness. As 2025's revelations, from weakening dark energy to AI-enhanced SETI, unfold, they deepen this paradox, urging humanity toward bolder probes of the stars.